Yonatan Geifman, CEO and co-founder, and Ran El-Yaniv, chief scientist and co-founder of Deci. And Ran is also a professor of computer science at Technion University in Israel, one of the top schools in Israel. Welcome both to the Data Exchange podcast.
Thank you.
Hi, Ben.
Thank you, Ben.
Pleasure to be here.
All right, so I guess we'll start off with what is Deci and how did Deci originate? And I'm sure you guys will have very different stories about the origin story of Deci.
Yeah, so 1.5 years ago, we founded Deci together. Before Deci, I was a PhD candidate under the supervision of Ran. And after completing my PhD, we started to think what will be like the next problems to solve in deep learning. We focused both on deep learning research before that. And we thought that in 2019, people started to learn how to build deep learning models. But there's another barrier, another step to cross while making them work in production. And when we learned a little bit about the problem at industry of taking deep learning to production, we understood that we need to design algorithms that are better in some terms, like in their adaptivity to the hardware, in how they work in production in terms of latency or throughput. The total cost of ownership of these algorithms is huge. And we started to develop Deci to solve all these barriers on how people build, optimize, and deploy deep learning on their way to serve them in production, in a scalable production environment. So we started to develop our technology that maybe Ran will be happy to talk about.
Actually, Ran, before you answer, so Yonatan just described things that are very practical. That doesn't strike me as something that professors focus on.
Yeah, so actually I agree with this story. I think that behind all that, Yonatan and myself, while working together on Yonatan's research towards PhD, we felt that we would like to continue that after the PhD. So we decided to do something together even after completing the PhD. We consider several.
So as I mentioned, what Yonatan described seems very practical and not the type of research that you would see at NeurIPS or ICML. It's a little more practical, right? So was that really what you folks were working on?
Working on deep learning has a very practical aspect to it, and while I was used to doing theoretical research before going on to deep learning, you cannot really do deep learning without practicality in your mind. So we got used to that already a few years before deciding about establishing Deci. And being practical in this sense, it's very interesting also theoretically. Theory and practice here combines, because the main issue that we have to tackle is how to make architectures that neural architectures that work very fast but still very accurate.
All right, so Yonatan, let's organize the landscape for our listeners. So making deep learning run fast. So there's hardware, there's software, and then there's the models themselves. There's open source projects like, I guess, what's it called? Apache TVM. So, or just give us kind of a taxonomy of what are the different tools and components that are relevant here.
Sure. So we can imagine we're looking on deep learning inference stack, that we have several layers. On the bottom, we have the hardware stack where we see GPUs, TPUs, some dedicated ASIC, and we see a lot of startups working on new chips for deep learning. We see chips that are more focused on training and chips that are more focused on inference. So in our case, we are talking on dedicated hardware for deep learning inference, but it could also be hardware for like general purpose, like CPUs that need to run inference like we have on Zoom or consumer applications that run on our laptop involving deep learning. On top of that layer, we can see the drivers of the hardware, how, let's say, the model is utilizing the hardware based on the drivers. So the most known example is the CUDA drivers that are utilizing the GPU. On top of that, we have the graph compilers. Graph compilers are components that coming to compile a deep learning model in order to run more efficiently on the hardware. And it involves like memory allocation for the model and some optimization on the graph level like that. Graph compilers are remaining the model exactly the same in the sense of optimization, but it sets like the operations on the memory and control how the model is executed by the hardware. So all of this is kind of the hardware related stack. Also, we can see TensorRT, Apache TVM, and OpenVINO in the graph compiler layer. On top of the graph compiler, we see some open source tools and techniques that are also known in academia, like pruning and quantization. So quantization is simply reducing the bit width of the computation.
These are things like SqueezeNet and the old SqueezeNet.
I think that SqueezeNet is not necessarily involved with pruning or quantization, as far as I remember, but all the idea around the lottery ticket hypothesis paper from last ACLR and a lot of focus on pruning and quantization that make this deep learning run faster and consume less memory when they run.
But the key point here is that we're talking about a suite of tools, a stack. Right.
Yeah.
So and they all have to work seamlessly together. So Ran, in fact, when I talk to hardware companies, I've learned to ask them the question about software, because it turns out that hardware is not enough, right? So you can have a new hardware startup that purportedly accelerates deep learning, but it turns out they actually don't support all of the deep learning models.
What is the question?
Oh, so my question is, software is just as important as hardware, even for hardware companies, right?
Definitely so, yes. You can make the best piece of hardware to do, for example, inference or training, but without the appropriate software support and
community around your software.
You need a community in order to drive all this software to the right direction, and without that there is no chance that a piece of hardware will succeed to catch and be used and utilized in production. Definitely.
So Yonatan, we talked when we previously talked. I brought up the fact that actually a lot of people don't seem to appreciate that inference. There's a lot of compute that's needed for inference, right? So you look at a company like Facebook that makes, I don't know, maybe billions, trillions of inferences a day. So clearly, inference is something that has to be optimized, and you have to execute well on inference. And based on your description, it seems like it's also quite challenging because there's so many components and pieces. So what is the right strategy for evaluating or designing your inference stack? You know how companies now are talking about their ML platform or ML stack, right? So it seems like based on what you're saying, there's also a need to think about your inference stack.
Absolutely. So I started like a bottom-up description of the stack. But I think that the right approach is to think about it top-down. So you need to think first about the model. When you design a model, when you first build it and train it, you have to think what is it going to do in production? What chip are you going to launch it? What performance are you expecting?
From the beginning, you think about
from the beginning. Okay. When you choose the architecture or when you design the architecture for the specific solution, you need to think production. When you design it, before getting the accuracy, you need to think about what this model is going to be launched on, where is it going to work, what latency I'm expecting to reach, and Based on that, you need to choose the right model. Today, we see solutions like in academia that involve neural architecture searching for the right model in order to kind of balance the trade-off between the accuracy and the latency, or accuracy and the size of the model. We saw the efficient net papers, that efficient net paper that is simply doing that, like giving kind of a Pareto curve that showed the trade-off between the amount of computation of the network and the accuracy of the network. So Deci is simply thinking about this approach, about building more efficient algorithm. After you have a good algorithm, you need to consider all the stack below. And it also affect the algorithm. So one network could be run very good on FP32, but not compile good or quantized good to FP16, for example. So you need to consider everything, and it's an holistic approach. It's not like, okay, I will build my model and then I will tackle problems to getting it to production, because then you will fail taking into production under the SLA that you are expecting to reach at the end of the day. So this is kind of the holistic approach that we develop the Deci, and we think that this is the right solution, or this is the right approach to or state of mind to get faster to production and make deep learning projects succeed to reach their end goal to be a production services.
By the way, as you were talking, I was getting nervous in the sense that, a typical company right now, their goal is to take deep learning or even plain machine learning and deploy it to production. And now we're talking about optimizing for inference for different environments. So Ran, I presume then that this is why you folks started Deci. It's because the typical company may not be able to do all of these optimizations, right?
Yes. So, the typical story of deep learning company doing some application, they work very hard collecting the data, spending 70% of their time cleaning, recycling, cycling all these this vicious loop of building a model and collecting the data for that model, and then they reach the time that they have to produce, and now they have a model. It's working in the lab, but when you consider production without all these parts of the inference stack that Yonatan mentioned, it's sort of meaningless in the sense that if you don't consider graph compilation, suppose, for example, that in the extreme case that you cannot compile at all, then you're not going to be cost effective on the cloud, or maybe not real time if you're in the edge, if you do some vision application, for example. So this is very, very important to consider while designing your network. And we, as Deci, we meet these guys in a very convenient position for us, and also for them. And it's a win-win situation for both, because we take them the last few miles that are extremely hard to do, and you need a lot of knowledge and understanding of all these inference stack and architectures, which they didn't have sufficient time to consider.
So, Yonatan, actually, the other thing that, as you were talking, and I guess Rand confirmed this, is when I think of inference, especially on the hardware side, there's two types of hardware companies for inference, right? So the ones in the data center and cloud, and then the ones on the edge. So it sounds like you folks can help me either way, regardless of whether or not I'm in the data center or in the cloud, correct?
Yeah, that's correct. Our approach, on one sense, is hardware agnostic. So you can connect any type of hardware to our algorithm and optimize for a given algorithm to a given architecture of hardware based on a simple API that you connect the hardware and do concrete measurement on the hardware. And on the other side, we optimize the architecture to run best on a specific hardware. So let's say you want to run on edge device of Coral TPU. You connect the Coral TPU to the algorithm, to the AutoNAC algorithm, which is the neural architecture search that we drive. and it optimized the neural structure to be optimized to the specific scenario of doing inference on the Coral TPU for your given data and problem that you're trying to solve. So this is kind of how we treat hardware as a black box on one sense, and being able to be optimized to the hardware by simply connecting to it like via an API and optimize the network for the given hardware that you are going to use.
So give us a sense of some performance or ROI improvements in terms of, let's say, even some of the customers that you have. So let's say I have a cluster of CPUs and I'm already doing inference my way, right? So the default way, and then I start working with you. So what kinds of improvements and savings am I going to start seeing?
So
I guess it's very dependent on the model, but just roughly, yeah.
Absolutely. So let's begin with a well-known benchmark that we published on MLPerf last September. We participated in the open division together with Intel, running a ResNet 50 on a CPU, and we were able to boost it by 12x compared to a naive baseline implementation without any graph compiler compilation or anything. But when you take the state-of-the-art results that also Intel submitted to the closed division, that is utilizing graph compilation via OpenVINO, quantization to 8-bit, and everything that we know in the stack except accelerating the algorithm, and we use Deci to optimize AutoNAC to optimize the neural architecture, we were able to improve that in a factor of 4x. So this is an open source example that we published on MLPerf. If we'll take it to a customer, we have an example of a cloud video analytics company that we were able to accelerate their model by almost 5x. This reduces the cloud cost by almost 80%. So if you think about it, if a single GPU could process 5x more images per second, your cluster will be smaller on average by 5x, and it will reduce your bill on the cloud by a similar amount. So this could drive huge savings for inference workloads and inference clusters that involving GPUs and CPUs.
So Ran, is the technology of Deci is it around acceleration of the inference, but also I guess energy consumption and things like this. So the presumption of the technology is I have a model that I can deploy, but you can help me deploy it more efficiently. But can it help me deploy a model that's like economically infeasible to deploy right now? So I guess I don't know an example of this. Let's say an imaginary GPT-5, right? So where the model is so big, I can't deploy it, but can Deci help me deploy a version of GPT-5 in a way that makes economic sense, whereas the original model may be too huge and expensive to deploy? Do you foresee this technology being able to handle this kind of problem?
That's a tricky question because GPT-5
doesn't exist.
Probably hard to imagine what's the size of GPT-5. But the answer in principle is yes, and there is a race. The race is the giants show us huge models like GPT-3, 175 billion parameters. This is close to the number of, let's make a crude analogy, to the number of synapses of brains. So it's close to the number of synapses of a house mouse. It's huge.
Right.
And it's surprisingly huge. And the cost is enormous. Also, already to train that network is several millions of dollars only to train that. The inference will cost many millions all the time. So if we can reduce the price by the energy consumption and therefore the the cost of operating it on a let's say a number of GPUs on the cloud, then or CPUs, then by a factor of 10, this is a huge reduction in costs. So this race will always exist as long as we are progressing with technology. The giants will show us the big models. We will try to shrink them and make them more economic and available to other people by reducing the costs.
So Yonatan, same question, unfeasible to feasible.
I agree with Ran that the large models are here to stay. Like there is a gap between the computational abilities and the demand of these algorithms. So when in 2012, when AlexNet was presented, it was too large to fit on a GPU for training, for example. And since then, we see the more load that the GPUs are getting larger and larger and more capable. But also we see the algorithms that are getting more and more demanding in compute. So we kind of see a gap that is here to stay between the available compute and the demand of these algorithms. So this gap is something that Deci is trying to solve and to minimize in order to make a deep learning algorithm affordable and available for everyone.
Yeah, so Ran, are there any research initiatives in the horizon in the area of inference that we in industry should be aware of?
Wow, this is yes, definitely yes, and there are. I assume that there are thousands of papers, maybe tens of thousands papers in the past few years, and it goes along quantization, pruning. Although pruning currently does not help to expedite inference, and probably the most ambitious topic is neural architecture search. Where you can see hundreds of papers each year.
Which, by the way, I did a somewhat of a deep dive into NAS, and and this actually, in retrospect, makes sense, right? So if you take it literally, NAS, neural architecture search, they're searching through the space of all possible architectures. But really, and correct me if I'm wrong, Ran, I think what they do for the most part is they do some kind of, here's Yonatan's massive architecture, Ben will modify Yonatan's architecture a little bit, and then they do some kind of weight transfer, right? Because they can't really train all these networks from scratch. It's just computationally expensive. If the models are so humongous and each model costs $100 million or $10 million to train, you can only probably train one or two models, right? So explain to us, Ran, how does neural architecture search actually work from in practice?
So first, neural architecture search is not currently. Probably besides our AutoNAC algorithm, which is practical and commercially available for a cost, I'm not aware of commercially available NAS algorithm. Although you can see operations of NAS algorithms in Google and other companies, in big companies that can spend tens of thousands of GPU compute power to such an optimization, and they have wonderful results like mobile nets and efficient nets, which are really.
You have to use some heuristics, otherwise it gets expensive, right? I guess is my point.
Yeah. Yes. So originally, you can view NAS in several ways, and there are three different vectors in order that you can use in order to do NAS. One of them is a discrete search using some clever tricks like reinforcement learning or something similar to that. Another one is differentiable NAS, where you try to represent all different architecture using differentiable parameters and use the optimization, the SGD, stochastic gradient descent optimization in order to optimize. And there is a very interesting direction which is called once for all, where you train a very large network, and you also train subparts of that network, so that something which is similar in principle to dropout, but in the scale of a sub-network. Most of these direction, when you consider the result, like state-of-the-art results on very large data sets, they need a lot of compute. Our starting point at Deci is quite different. We start a search from a very convenient starting point. We start from an already existing network of the customer's network. Let's call it the baseline. And this baseline is, we copy some parts of that network to the target network that we're trying to optimize. For example, the prediction head is kept initially as it is. And we already know what is the accuracy that we would like to achieve. We are optimizing something else, like inference time, which is latency or throughput or power consumption, but subject to preserving the accuracy. So
it sounds yeah. So I guess it's NAS, very practical NAS in the sense that you assume that I have a model and you trust my model, and then you're going to help me deploy it more efficiently somehow.
Yes,
right?
yes. Essentially, we are going to redesign the bulk of your network, which is sometimes called the backbone. So we're going to replace it with a very efficient backbone, and keep the rest the same. Keep your training regime the same. So we don't really need to look for extra things which are not needed to do this task. So we are considering a restricted type of NAS, and this is why we can do it extremely fast.
So, Yonatan, at a high level, again, I'm asking you these impossible questions, but this is what podcasts are for. So at a high level, software and hardware, right? So you've got all these hardware startups for inference. How much can you get out of hardware, and how much can you get out of software? I guess by how much, I leave it up to you to answer. How much improvement can you expect to get out of hardware and software? Yeah,
that's a good question, because it's not an apple-to-apple comparison. But
yeah.
Apple is hardware is advancing all the time. We see better GPUs, better chips for the edge, etc. But also algorithms are getting better and better. So if we'll compare like the AlexNet or VGG from the early days of deep learning to EfficientNet, or some of the most efficient architectures that we see today, there's a huge gap in terms of the trade-off between accuracy and latency. So if we kind of draw the efficient frontier of these algorithms, we see that VGGs and AlexNet and even ResNets are not as efficient as possible, like the newer architectures that we have today. So we believe that on the algorithmic side, there is a lot to do, because deep learning is evolving all the time. We see new optimization techniques, we see new types of architecture, and there is a lot to do from the algorithm side. But we are not alone in the race. Like, there is the counterpart of the hardware that is advancing all the time. But the main message here that it's orthogonal, in the sense that every advancement in the hardware, without the right algorithms, will not be able to utilize. So they are working together. How algorithms should be optimized for a specific hardware to better utilize the hardware, and these need to be co-designed. Like, the given hardware should be involved in the development of the neural architecture, in the development of the architecture, in order to get the best results.
So the hardware inference startups that are in the data center, that focus on the data center, I guess who would this be? Like Habana, I guess Cerebrus to some extent. So what does your software work with these newer hardware?
Our software works with every hardware that has a generally available API or software stack. So if it could run an ONNX, a PyTorch, or a TensorFlow model, we can plug this hardware to work together with our AutoNAC algorithm. So this is our only requirement. So in terms of integration, there is zero integration since we are looking on these hardware as black box. We just need to be able to connect and run neural architectures. In some cases, we see very weird hardware where there's a lot of constraints, like on the size of the memory that you can run on, and the supported operations, the supported neural network operations that you can run on. And we are adapting the algorithm to search in a constrained search space that involved only architectures that are supported with the hardware. So any constraints that are given from the hardware could be implemented or could be integrated to the search algorithm, to the AutoNAC search algorithm, in a way that will find architectures that could fit on the hardware and run on the hardware. So this is kind of the main idea of automatically finding architectures that works well and efficiently on the given hardware.
So Ran, in terms of research and theoretical underpinnings of what you folks do, are there certain architectures where your approach won't work necessarily? So you know what I mean? So it's I guess it's some sort of optimization problem which you have not found an efficient way to attack yet. Like, so here's an architecture, here's a model that maybe we can do a little bit of, we can make you more efficient, but we can only get so much.
That's an excellent question. So theoretically, let's say that you have, you're holding, so let's make this question more well-defined. So good architecture always, as Yonatan says, always has to be associated with a certain hardware. It's meaningless to say, I have the best architecture at all. You have to say, this is architecture for, also for the data, and the hardware is very crucial here. Also, the data is crucial because
so I have the best architecture for this hardware, but
yeah.
I want to deploy to this other hardware.
And, so here is a lower bound. Here is a lower bound. Say that you have the theoretically optimal architecture among all possible architectures, running, achieving a certain slice of accuracy for a certain hardware. Then we cannot optimize it, and nobody can. However, the space of all architecture is enormous. It's like 10 to the 22 or so.
But can you get me within 10% of my error rate, but reduce my number of parameters by 50%?
Sorry, I didn't get that.
So is it possible to do, you know, I have a model, and then I ask you, hey, reduce this model's number of parameters by up to 50-60% while keeping the error rate within 10%. Is that always possible?
No. So what I started to say, that there is a lower bound. If you Ben, you are holding the best architecture for a certain hardware device, achieving a certain accuracy. If it's optimal, then nobody can do it. But what I'm saying is that it's extremely unlikely that you have that model, because this search space is so huge that it's very hard to come by this model. So in almost all cases, we will be able to do something. You know, it's very hard to make Olympic runner, to find someone that runs faster than Olympic runner, but it's very easy to find someone who runs faster than the average person. So in almost all cases that we expect to encounter, we will be able to accelerate.
So Yonatan, for what you folks do at Deci, are you more focused on edge or data center?
We're doing both. I think that the value proposition is a little bit different between the data center and the edge. In the data center, we see more cost issues that people want to scale their services and the cost is enormous, and they call us in order to make the cluster more efficient, reduce the computational cost. And in the edge, we see more and more companies that are unable to deploy their models to the edge devices because of unsatisfying latency. So this is kind of the two pillars of our value proposition. At the moment, we see more and more demand for computer vision on the edge, but also the cloud is growing. The usage of deep learning and deep learning inference in the cloud is growing all the time. And we see also there like a huge demand for optimization and reducing the cost, because companies are scaling. Companies that are using deep learning are scaling at the moment, and they need to consider solutions to reduce the cloud cost for the deep learning cluster.
So in terms of use cases, is it mostly computer vision at this point?
At the moment, we are mostly focused on computer vision, since we see more solutions out there that already using computer vision in production compared to the NLP space, which is a little bit more new with the transformers that appeared in 2018, and computer vision is here like for the last 6 or even 8 years. So basically, we see more and more demand for computer vision, but soon we will be also tackling some NLP problems, mainly in the cloud. So if we need to segment the market, we see like almost equal demand between computer vision and NLP. The computer vision is kind of 50-50 split among edge and cloud, while the NLP is mostly in the cloud and the data center. So this is kind of what we see.
So NLP in the cloud, can I get by without Deci? I mean, I'm in the cloud. I have infinite compute, and it's unless I use GPT-3, a conventional NLP model. Maybe I can just get by without using Deci.
You can do it, but you can't do it in a scalable manner, because at some point you'll have to consider the cost of these algorithms. If you're Google, you can run a BERT model for every query in the search engine, but most companies are considering way to accelerate and reduce the cost for the deep learning inference that they are using. So you can go up and do serving for NLP models in the cloud at the moment. By very quick, you'll get to a point where you'll need to consider solutions to accelerate and reduce the cost.
So Ran, last year, a group of researchers at MIT published this paper on the computational limits of deep learning. Particularly, so they had a team of computer scientists and economists. So basically, they took a domain, for example, let's say computer vision, right? So where you now have closing in on 10 years of history of progress in the field, so they could model how much error rate improves over time. And then they started plotting the amount of compute. And this paper is kind of scary, you know, as you start lowering error rates to what they are currently now, the cost of achieving those improvements, if it holds to historical pattern, is going to be enormously expensive, and because it's expensive computationally, it's also expensive environmentally. So are we at the point where we need to figure out other approaches beyond deep learning?
This is I haven't read that paper, but I see exactly what you mean. But there is another point to it. Let me just first relate to going larger. So going larger at the current rate, exponential rate of technology improvements, is not sustainable. In the sense that if we go on like this, all the power consumption in the world will be dedicated just to deep learning. And this is not going to happen. So something must change. And as always, what comes to rescue us is different technology. So we expect different technologies to come along. So this is one aspect related to going larger. But there is another aspect of going smaller. And we see a trend of tiny ML. trying to operate machine learning, deep learning on very, very small devices. And these devices, and in order to be productive and do something useful, they have to be accurate. And so the machine itself should be sufficiently strong, and designing the algorithms to do the
But Ran, tiny ML is practical. The race towards exponential growth is aspirational, right? So for AGI. So is there a way to get to AGI without global warming?
So, well, it's very easy to make foolish predictions, especially about the future. So, what I believe, personally believe, I don't know if Yonatan believes as well, but that something new in technology will come along, like graphene transistors, neuromorphic computing, something else, going along exactly on the same vector is not sustainable.
But what about, so I was hoping you would say new modeling techniques.
So new modeling, the appetite is going larger. We see the GPT-3 and we want to have it on our phone.
But there might be, Rand, there might be a group of people that are conducting model search in a different area in the space of algorithms, not in the area where deep learning is, right?
Okay, so we have an example, a very good example, and this is our brain.
Yeah.
So in order to, if GPT-3 is roughly 10 to the 12 weights, and a cat is 10 to the 13 weights, synapses. This is a very crude comparison, and people will not agree with me, but just to make the argument. And a human brain is 10 to the 14th. And Moore's law tells us that every 2 years we double the number of transistors for the same cost. So
so some people say Moore's law is dead. Some people say Moore's law is dead.
So in 10 years, for example, we will have 2 to the 5 increase. It's 32x. So we need like 20 years in order to do something really, really meaningful, which is close to the human brain. But it's probably not going to progress exactly in the same, using the same technology.
So Yonatan, a typical company, I guess I wanna close this discussion by going back to this notion of the AI inference strategy. You have your AI, you have your ML ops strategy. So AI inference strategy. So what are some concrete steps that someone can take to get started to optimize their inference strategy?
I think that the first thing is to understand what is going to be the cost or the latency of the model in production. So first thing is to benchmark. After you benchmark, you might find out that you don't need it. Okay, you have a model that is very small, working on CPU because you're solving a very simple problem, for example, with low resolution images or something like that, and you're good to go with your model. So first of understanding the problem is the first step in order to solve it. In most cases, you'll find out that you have a problem with the inference.
By the way, as you said that, it just occurred to me that maybe that's something even the product managers should do up front, right?
We talk a lot with product managers that have Excel sheets that they show, okay, how many demand I'm going to have, how many nodes in the cluster, what is the cost, calculating the cost for the entire month. So we see product managers that are doing these benchmarks. So, but the first step, even before you want to go to production, is understand what the architecture that you chose right now, what will be its cost.
If I get this many users, if my number of users grows, right? So start modeling that.
So this is the first step, like understanding the problem. Next step is you can use some tools that are open source, so you can get them by our platform, our community edition of our platform. So these basic well-known techniques such as graph compilation, quantization, and techniques like that, this is kind of the lower level of optimization. But if you want to go further and you want to get the best results because you're working on real time in the edge, or you have a very large scale in the cloud, then you need to go to optimize the model itself. So most people try to remove layers, change the size on the layers, and enter into a trial and error iteration of finding like a model that is a little bit better, a little bit smaller, and that still preserve the accuracy. But we have a methodology to do that automatically via our AutoNAC algorithm. So simply that's the way to optimize the model itself in order to get the production performance that you're interested in.
Actually, one final question, Yonatan. So in your mind, what is the level of awareness among the people you talk to in industry about the need for this inference strategy, having an inference strategy?
It really depends, because you might talk with startup that still developing their solutions, so they don't have models in production. But I think that 80% of the people that have models in production are aware of the problem, of the costs, or the latency of serving those models, and also the complexity of the technical aspects of taking a model to production. So everyone who crossed this barrier and know what it takes to get a model to production, and aware to the cost or the latency of this model in production, and thinking about optimizing their model. So if you got there, you know the problem.
And with that, thank you, Yonatan and Ran.
Thank you very much, Ben.
Thank you very much, Ben.